I'm going to summarize my PhD thesis that I defended in December. So the title is the incorporation of geophysical, petrophysical, and geological constraint in gravity modeling to resolve structures at depth. And also say thank you for the partners. So the motivation for my thesis was to provide a better sense when you are constrained either a, let's say, gravity model or magnetic model. Because you have this non-uniqueness problem, so you have to constrain in order to have a better model. But sometimes we see like papers that say the model is constrained, but sometimes just one of the parameters is constrained, the other is not constrained. So that's the reason for this research, try to provide a better sense in how much every constraint that you incorporate in your model, how much is going to get a better model. So in other words, so demonstrate how a model either inverse or forward is improved as new constraints are incorporated into the gravity modeling workflow. And these constraints for this case is included data from gravity uncertainty analysis, which we usually don't take as a constraint, but we can use, and I'm going to show you. Density compilation, high resolution seismic sections, geological maps, as well as geological interpretations. And it was done at the Madison area, which Said talked a little bit today, and focus on the Porcupine District fault, which is a crustal scale fault that's also associated with a number of gold deposits, so have very important economically, this fault. So the outline of my presentation, so I'll talk a little bit just about data acquisition reduction, later on a little about error analysis, and I'm going to cover the Porcupine District fault deep variation, focus on the Porcupine assembly, and later on it will be more focused on from unconstrained to constrained inversions by adding constraints to get a better model. At the end, hypothesis test, is there a deep Delors assembly? Said also mentioned something about this in his presentation today. So the gravity data reduction, the data was acquired in 2018 meteor field season. We can see in this map here is a very simplified geological map, but we have this, I believe, black dots, I guess, dots. We can see all the way the gravity station. All of these profiles are crossing the Porcupine District fault, which is here, all the way from west to east here. The spacing was 300 meters between stations, and the survey was tied to the Canadian Gravity Standards Network, which is important because later on I'm going to show you that we combine this survey with the historical surveys that is compiled by the government. And here in this picture we have the gravity meter, as well as on the left the GPS receiver. So the data reduction pretty much standard, so I don't have to mention, but it's pretty much the standard for gravity data. And so the first thing that we have done was make sure that this data is suitable for the things that we want to understand. So as we can see, for example, in this example here, so there is fluctuation in the gravity measurements, either the gravity itself measurements or the GPS measurements. So we have to take into account, and that we actually estimate for two ways the error propagation equation, which is very common like for lab physics. So the important thing for error propagation equation, we can estimate the uncertainties or error for every correction that we apply into the data. And the other way, which is much easier, faster, and not time consuming, is by just compare measurements at some stations that we reoccupy and we acquire more than once that station. So we compare both, and they're pretty much consistent. So we are going to use this For complete Boolean anomaly, 0.121. And what does it mean, this uncertainty in the data, when we take this uncertainty into the model? So that's this first constraint that we have. So for doing this, we have like we have a smaller area just focused on the porcupine disturbed fault. As we have at the north, the porcupine assemblage, which is lower density than the lower Tisdale at the south. So it allows us to have a difference in gravity measurements. So we select at the south of the porcupine assemblage, so these three profiles here. So we have on here on the right, we have the petrophysics, the density compilation for porcupine assemblage and for lower Tisdale. And also we have the seismic section here that was important because we also can interpret this reflect as the bottom of the porcupine assemblage, which is one constraint that we are also introducing in this modeling. And pretty much the thing that we are trying to get is, okay, there's also assumption that the fault is linear in this simplified model. And okay, we have 0.121 milligauss uncertainty. So we take this into the data, let's say, and by just adding a noise, like a controlled noise based on the uncertainty, which was 0.121. And pretty much any of these four, which you can see here, but we have much more actually statistically have done. So can see our measurements because there is uncertainty associated. So in this panel, we have like 4 examples, like the observed data plus some noise data set that was added. Okay, and here is the dots are the observed data plus some noise, and the predict data based on, for example, in this model here. So which angle here is going to have the low misfit here in red will be our the porcupine disturbed fault dip. So, and by doing statistical analysis, we end up having these uncertainties for the fault itself in assumption that the fault is linear. So for this section B, so 28 plus minus 1, C 54 plus minus 1, and for D 45 plus minus 2. So that 0.121 milligauss means that we're going to have this uncertainty in our model when we take into account that error. So that's pretty remarkable, and we can say, okay, let's use this. What happened if for the same area, giving the same density values for both unities, but let's say if the complete Boolean anomaly uncertainty or error will be like 1 milligauss, which is very common for regional data set compilation. So we pretty much were not able to estimate the porcupine disturbed fault angles if you were doing this assumption. So it does show how important to have like a good data, and also how important when we know how sensitive our model is based on the data. Okay, and moving on, we have this, okay, now we are very comfortable in terms of the data uncertainty, so we move on and get not only the porcupine, not focus only in the porcupine disturbed fault, but also the porcupine assemblage. Think about depth of the porcupine assemblage, the thickness, sorry, and also the pipestone fault, which is this in blue here, all the way from west to east here. So on right, we have this high resolution seismic lines. So for A, B, C, and D. So this is A is Shillington line, B is Valganier, and C, Warabig, and D is Madison, which Said mentioned before, was focused on this part, by the way. And okay, and moving on, we have these 2D models for this area. And we can see here the Porcupine District fault now is no longer like a linear fault. And we use the magnetic data just to locate the dikes, because we can see some dikes crossing, not this, are not located like this south-north dike, but this, they're crossing, cross-cutting the profiles we added into the model. So, and here is the gravity data, the first panel, the model itself, and the seismic interpretation, here, seismic section with its interpretation. And we have like this 3D view for the Madison area. So the Porcupine District fault is deep in south, as we can see here. And we also have some idea how like the Pipestone fault is in terms is a more vertical comparison to Porcupine District fault. And okay, but the Madison, we had the R1 seismic light, the low resolution, it's cover a bigger area. So before we are just focusing this part, but now you get this like bigger area where the seismic line also cross-cutting this Big batholith. So, but the thing is, when you take a look in the seismic section, we only see some very deep reflectors like this A, B, and C, right? Like Said has mentioned about B, we're gonna talk later on about this. But okay, we still have to rely on this gravity modeling in order to understand like shallow and features. And so now we're gonna start doing 3D, start from unconstrained and going towards constrained inversion. So before I show you for our model where like the person that is like operating the algorithm is the software is changing manually your model. So when you have an inverse model, like the algorithm is doing this for us. So here on the left we have all of the station. Now we combine in blue the Metal Earth station and in black the Canadian gravity database compilation. And right beside you have the free air gravity anomaly map, and here a simplified geological map with its unities. And also here some parameters for the inversion, so the 25 kilometers depth, and also some other important parameters like the size and also the mesh size. So, and we use VPMG algorithm for the inversions. So the first model that we have is purely unconstrained inversion, and the thing is like it's the good thing in using like unconstrained inversion because it's very easy to get low misfit. It's not that is also quickly to get this. So as you can see in this plot, so we got from something like about 30 milligauss to 1 milligauss, what was the goal. And like when you compare observed data and calculate data, it's very good, right? So in the residual here. But what we can get from the model, so we're gonna be focused on this part because we have more previous study in the Porcupine assembly. And you're gonna focus on this part to see, in compare and see how reliable are this information, how much you can get from this model. And when you compare, this is just a zoom in that part, just change the color palettes, so try to match the Porcupine assembly here in this geological map. And when you have this, and like, because when we are doing an inversion, we try to resolve in the case of gravity inversion, you try to resolve this density problem, the geometry of the source, and also the depth of the source. So for this case, I'm gonna get the depth of the source as the thickness of the source. So in compare this to these previous studies, which is just interpreting the Porcupine assembly much more thinner than with this inversion that get like about here 10 kilometers thickness, and here is about 2 kilometers. So it seems that it's very thick, right? So, and also the petrophysics problem is not resolved. Is about 2.663 or something here. And when you see the petrophysical compilation where we took samples and could measure, so it's about 2.73, right? And okay, we can do some improvements in the model, and in this case, still focus on the porcupine assemblage and still using these previous studies for supporting this. We can do a depth weighting, and we can make like the porcupine assemblage thinner by adjusting the zero in this equation. Okay, and now we can use this. We can see. Okay, we know this, by the way, is Shillington line. So we can using this information and checking other parts of the porcupine assemblage how thick is porcupine assemblage. So we can kind of get improvement here. We still cannot rely on geometry, but we can, if you want to know, for example, okay, how is get thinner or thicker, you can pretty much understand this. But still, we didn't resolve the petrophysical problem for at least for any of the units, but we can focus on the porcupine assemblage. And just by changing the starting model of the inversion, we can get something closer to our actual samples that we have in terms of density. But still, we didn't resolve for the other units. We did constrain the geology at the surface, so we end up having to do a constraint, doing geometry inversion. So in the geometry inversion, we have this starting model. So very simple, just 3 units. And in this case, we are constraining the geology at the surface. So saying the contacts are not allowed to move. They are allowed to move, though, at depth. And the density also are fixed based on the petrophysical compilation, which here on the right we can see all of the place that the samples were taken. And here just the average and 1 standard deviation for every unit in this area. And this is the start model, right? So we have all of the units assign a density value and the same thickness for all of them. And okay, and we have this geometry inversion, but we constrained the geology at surface. We constrained the petrophysical or the densities, but look, the misfit was not that good at all, and also the geological likelihood to have this model is not something that we expect for this area. So we have to do something else. And the way that we found out was, remember this was a model that I showed before. So we have these 2D models already. So we use these 2D models that we I showed before and create a 3D model just by joining the contacts of the porcupine assemblage. So we have here from these 2D models, these 3D models. And in this case now I can use the porcupine assemblage to kind of anchor my inversion. So the contacts, the outer contacts at least of the porcupine assemblage are not allowed to move, only the inner contact with this intrusion here. So, and let's see what we can get from this. And by doing this, we got a better model. You can see here, we have something more realistic in terms of not all of the units are like the same thickness. And here is just a density model with all of the density values associated with and a geological units associated with those densities. And also the misfit is much better than before. It's about 2.43 milligauss. But still, we can still improve this model because the variability of density in each unit is not like one value. It's not like just average. You can see for variability batholith. So it's quite there's quite variation here. So we take this into account and let the algorithm doing a property inversion. So some of, as you can see, for example, for variability batholith, you can see that they slightly change a little bit the blue tone, right? And also the misfit, you get something close to 1 milligauss. It's not that bad. And when you compare the observed data, calculate data, it just is very good, right? And the model itself, it's much better than before. And just like something that we realized later on, like maybe this A, there's a good chance this A reflector that you showed before to be something the bottom of some part of the water big batholith here. And about B and C, we'll talk later on in this presentation. So just summarize something related to, let's say, like the title of my presentation. So we have like unconstrained version. Okay, you have a good misfit, but like geologically doesn't mean that much in terms of results or interpretation. So we improve. Still, by doing that, we added the misfit. Okay, it'll be the same, pretty much, right? But we kind of improve something geologically in terms of interpretation because the porcupine assembly thickness now is more appropriate. Okay, moving on, by doing depth weighting and change the density for the starting model. Okay, the misfit will be the same, but like the geological and interpretation and in terms of resolving the density property and it will be better. So, but then we move to geometry inversion, and we kind of get a really bad misfit, and geologically unrealistic. So we kind of it was bad, we improved, now is bad again, and okay, we add density property, surface geological contacts, and scientific data. It's still not that good. Have some improvement, but it's not that ideal yet. So, and at the end, we just was able to manage and add the variability of density property, and we got like a better final model. But and I mentioned before, there is this hypothesis Said mentioned before when he was showing a seismic section. Is there a deep lower assembly at Madison? This seismic section is the Madison, which was the same that Said showed us before. So based on this previous study, this reflector here could be the lower assemblage, the top of the lower assemblage. And we kind of see in the other seismic sections something that it seems to be correlated. So let's reinterpret the seismic sections and see what happened in your density model, right? So in terms of misfit, in terms of what results we can get from this. So here we are comparing this scenario here where we don't have the lower assemblage underneath the lower Tisdale. And on the right here, we have the lower assemblage, which is lower density than lower Tisdale based on these samples. And so we have this for the same seismic section that I showed before, but now we're reinterpreting. Before, for example, this SR3 was the bore of porcupine assemblage. Now the porcupine assemblage is thinner. And it's the same for this part here. And it's in agreement with previous study, right? So it's supported by other studies. So, and here we have the same thing like here, but just to highlight the porcupine assemblage. In comparison here, in this case, when you have the lower underneath, it becomes thinner to compensate this lack of mass that we have here. So we have to make the porcupine thinner. Okay, but still, when we compare the misfit for these two models, they are pretty closer, but at least the Deloro case, we have some geological interpretation to rely on that. And we also did the same for petrophysical inversion to compare, and both are similar, the same misfit, 1 milligal. So when you just take a look at the misfit, you cannot tell too much, but as before mentioned here, the case of Deloro, by introducing the Deloro in this model, we have the porcupine assembly thinner, which is supported by previous studies, and which means even though both are the same misfit, but this model on the right, we have more information more previous studies information, geological interpretation. And in comparison, when you compare both cases here, so we have looking west and look east for just porcupine assembly, when we take in the Deloro, when we don't have the Deloro, so pretty much as I mentioned before, when we have the Deloro, the porcupine becomes thinner. But in terms of porcupine distal fault deep, it doesn't change that much. Here, it's going to change a little bit more at the west, because the top of Deloro, there's angle. But when we have, for example, in Madison, the Deloro is horizontal and doesn't change. Pretty much is when you have Deloro, no Deloro, the Madison will be the Madison, the porcupine assembly at the Madison will be pretty much the same. And also here we have three different scenarios, three different level of assumptions, level of constraint, and pretty much the porcupine distal fault is also dipping pretty much the same angle to south. So, and consistently, the angle for Valganier is lower than Warabi, which is higher than Madison. So they are very consistent in these three different, not different scenarios, but in different assumptions and constraint. So as a conclusion, the geometry of subsurface features, the depth of interface, and our density of regions can vary significantly in a subsurface model and still explain the same gravity data. So it's very clear when you have this hypothesis test and we take the Deloro or not. So we have, in terms of misfit, they are pretty much the same, but they are different, right? Which is the non-uniqueness case, so which always we are talking about. And the constraints apply to deal with this non-uniqueness. So you apply these constraints, and which one was the data uncertainty. You make sure that the data is consistent with the things that we want to get from the model. Data compilation was also important to make sure the density in the model were consistent with the physical properties of the rocks in the area. The right resolution seismic sections, although sometimes we couldn't see features that we want to see, it would be great if you could see, was able to identify some reflective features, most likely lithological contacts, and also information from previous studies was very important. We can see, for example, when we rely in previous studies in terms of the porcupine assemblage thickness, and also the Deloro hypothesis test. And a very important thing is we always talk about misfit, and misfit might be used as a guide, but it's not the only information like you have to use. Because if you only use misfit like an unconstrained model, it would be the best one, right? And porcupine distal fault was modeled in 3 different levels of constraint assumptions, and results are consistent. So if it's very consistent that the porcupine distal fault at the Madison area is deep in south. Suggesting, as just repeating, the PDF is deep in south and change along the strike, deep at the shallower angles towards west. Okay, that's everything that I have.